Вот. Да. Посмотрите, да, что мы сейчас только. Ой. Вы тут не успели. Сейчас, а почему тут? Откуда тут Windows? Да, ну давайте я напомню, что мы вывели из теоремы Хаббуша, ну, вот, просто вот в качестве лемма, которая у нас... Ой, секунду. Вот, пусть G, соответственно, геометрически редуктивно. Это значит, да, что у нее есть вот этот инвариант, инвариантный полином, который, соответственно, отделяет вектор, ну, не равен нулю на инвариантном векторе. Вот, соответственно, G действует на алгебре рационально. Ну, давайте я напишу лучше локально, конечно. Вот, ну и внутри G неподвижный идеал. Вот, тогда, ну, то есть, который переходит в себя при действии G. Ну, вот если F у нас элемент в инвариантах на факторе, да, то есть множество. То есть мы берем функцию инвариантную на подмногообразие, которое задает и, да, тогда на самом деле, что она приходит исходно из инварианта G. Но это на самом деле неверно. Это было бы так, если бы у нас была бы полупростая, ну, в смысле, настоящая редуктивность, то есть полупростота представлений. А так у нас есть ослабление, что для некоторого n, в степени, ну, для некоторого, да, как бы, ну, давайте напишу, для некоторого n большое. Вот f в степени p в степени n принадлежит как раз фактору r по g по и по g. Да? Вот. Но как бы, как мы это будем доказывать, ну, то есть идея, да, в смысле теорема, которую мы собирались доказать, теорема, что если G геометрически редуктивно, да, ну, характеристика P, да. Вот, если G геометрически редуктивно, то, соответственно, RG конечно порожденная алгебра. А если, ну и соответственно, если у нас есть m, это Ньюторов модуль, R-модуль с действием группы G, тогда МЖ нетров над РЖ. Ну, над алгеброй вариантов. Да, для чего мы упомянули? Конечно, нам в основном интересен вопрос первый, да, но вот эта вторая часть, она нужна, чтобы можно было, ну, как я говорил, да, напомню, что у нас будет схема доказательства, то есть из каких фактов вообще у нас будет следовать порожденность, то есть это в целом называется неутровая индукция. Вот, соответственно, она будет сведение к, ну, то есть это индукция по размерности, ну, то есть как бы она применяется к модулю M, да? То есть она для M и применяется к размерности носителя. Ну, второе число компонент, индукция по числу компонент носителя. То есть переход еще к неприводимой компоненте. И отдельно, ну, как бы у нас будет доказательство, когда компонент, ну, то есть вот доказательство для неприводимой компонента, то есть опять же индукция позволяет свести, ну, дальше шаг индукция, шаг сводит к модулю с меньшим носителем, ну или алгебре. Вот, ну давайте постепенно реализовывать свой план. Но вот в прошлый раз мы обсудили, как сводить, если у нас, то есть алгебру R можно считать, давайте, алгебру R можно считать градуированной. Ну, грубо, дайте я просто напомню, как бы, что из-за того, что x можно вкладывать в афинное пространство с линейным действием, просто, ну, мы выбираем набор образующих и помещаем в G-инвариантный модуль. Вот, соответственно, ну и как бы, да, при этом модуль M не считается, не является градуированным. То есть, как бы, ну, грубо говоря, мы x-то вложили в векторное пространство, но пучок, он не вкладывается как, ну, в эту алгебру. Ну, в смысле, он является пучком на v с носителем внутри x и не является градуированным объектом. Поэтому, как бы, это неудивительно. Ну, в смысле, что мы с помощью вот этого push-forward, да, можем поместить пучок на v. Да? Вот, соответственно, но давайте считать, что как бы первое, что можно считать, ну, первое сведем к случаю, сведение к случаю, когда RG, соответственно, область целостности. Вот, соответственно, R без кручения над RG. Ну да, тут как бы, да, проблема в том, что может быть, R область целостности, она подкольцовывая, R могут быть все равно остаться импотенты. First, so we are proving that if so we are now in characteristic P. Yeah? So we assume Mumford conjecture or Habush theorem. So as you can reformulate it in the following way, that if you have a reductive group over the field of characteristic P. So suppose it acts on the algebra and you have G invariant ideal. Then if you have a polynomial f, so a function f in the G invariance of R modulo G, then there will be some n such that the power of this element will be inside G modulo IG. Yes, so of course it is clear that this thing sits in the upper thing. This inclusion is trivial, but this, this is some kind of generalization of semi-simplicity of representations of G. So we are proving the theorem that if you have finitely, so if you have the algebra of invariance is finitely generated over K, and if you have finitely generated module over R, then MG is also Noetherian over RG. Okay. Yeah. So we are just we are considering reduction to the case when RG is the main and R has no torsion over RG. Yeah. And then you have the following. So suppose you have F that inside RG, which is a zero divisor in R. Yeah, so precisely when yeah, so of course the first it is clear that the first follows from the second one. Yeah, so that we're just proving that so we're doing a reduction when you have zero divisor for in the ring of invariance. Yeah, so zero divisor. Yeah, so for R. Yeah, so then just yeah, so then first of all we can assume, so by Noetherian induction, so you have, I shall explain a little bit later what you have for modules. So you can consider RFR over G. Yeah, so and it's the quotient R modular annihilator of F G invariant. So meaning that I'm just writing down R so multiplication by f, yeah. So first is here this you have cokernel, yeah, so which is R modulo RF, yeah. And you have kernel. So you have image, so this is image R modulo annihilator, yeah, it's just image of f of y. Huh? So so let us apply lemma. Yeah, so we assume that. So since you have so you have several. If you have R, which is a domain, then it means that you have several components, and f is precisely it says so the existence of f says that f vanishes on some of these components. Yeah? So f vanishes on some of the components as it is zero divisor. So you have this is a quotient just where so the equation given by additional so vanishing on f, and this is just the complementary set. Yeah. So we are applying lemma. Yeah, and by induction we may assume that these are finitely generated. Yeah, because there's so about the number of components. So applying lemma, we get that.
So what did you say? You say that our quotient by annihilator is have less components of what? Of reduced components, or what? What do you mean?
Irreducible components.
Uh-huh.
Yeah.
Ah, okay.
So this is actually a submodule, and you may assume for all submodules that I mean, so I shall formulate also explicitly what does it mean Noetherian induction for modules separately, and we shall see. So this is just a submodule of so proper submodule of R. And this is proper quotient. Not really. So, so we're applying lemma to our functions and to our rings of invariants. So you have two invariant ideals. And so you get that this set of invariants is so if you raise it to some power, it will be a subset of the corresponding set of invariants. And in the same time, this is a subset of R modulo FR G. So you have that so we have bounded this set. Yes, so we can assume Noetherian property. So we get from Yeah, so from this we can assume, so from this RG modulo FRG is finitely generated. Algebra. Oh. Yeah, so notice that sorry, here you have, so f is actually invariant here, so FRG is also, so it is isomorphic to, so precisely taking R modulo, so it's an image here of R, so it is R modulo annihilator of F taking invariance, and so it is also an theorem RG module so this implies by induction that RG is also Noetherian RG module, so it is Noetherian ring. So here you have to notice that this implies, so this implication, so let us see this implication, so that this implication is just due to the graded property. I mean, it's not so since we derive it since R is graded, so it's graded, and R0 is just K. So it's graded with this property. So if you have indeed, so if you have RG is homogeneous non-unit, so we assume that R more GR is finitely generated. And also R mod RG mod this element Yeah, so it decreases. So you have the element and both things just reduces to the case that so has smaller dimension, smaller support or smaller support. So it's finitely generated, and this thing also finitely generated. So yeah, actually yeah. So now yeah. So as for this, this is all here. I mean, so Noetherian property implies that this is finitely generated because of the following. So how it is done? I mean, so let us. We shall do it in the next step as well. I mean this argument. But if so suppose so also I want to keep track on the case. So also so suppose G is now non-zero divisor. So assume that G is not zero divisor. Yeah, so then this means that it has the set of zeros. Yeah? It's non-trivial, so this is this has smaller dimension. And if it is and also you have in the case when G is non-zero divisor, the multiplication by G, you can put it out of taking invariants because there will be no elements. So this is a subset of R, and yes, so you won't have elements that are annihilated. So this is just a G, R, G. Okay. So and if you have I mean since if you have action of the group, yeah, so H acts on the element of G, yeah. H belongs in the group. So it's you are acting by the group on G and F, and so you will have the property that G times H F. Yeah, so I mean since G is invariant, so you will have the property that GHF is equal to GF for any H element in the group. Yeah, and you will have, yeah, so I shall put a circle for action, and of course this implies that G H F minus F is equal to 0, and since G is not zero divisor, so this means that HF is equal to F, so F is invariant. Yeah? So you have this property, and the idea is the same as you have in the proof of the theorem in characteristic 0, because you can consider, and here we use the graded case. Yeah, so we can consider ideal, graded ideal. So this is RG plus. So this is ideal generated by graded elements, graded of positive grading, yeah, and strictly positive. grading. So by assumption, by induction, so you can pass to I modulo GR. So is finitely generated ideal in R G modulo GR. G. Yeah? So you get so I is finitely generated ideal in RG. Yeah? And so, yes, so this graded ideal is finitely generated ideal in RG. Yeah? And this is precisely, so we take generators and take homogeneous generators. So we pick generators of G. Of I, and you will pass to homogeneous and notice that precisely here we also use, so here we have obtained that RG is an Invariant ring over this. Yeah? So if you have zero divisor, yeah, so we have, and if we do not have zero divisor, we can pass to the quotient and see that I is finitely generated over RG. Yeah? And if I mean that we're proving finitely generatedness for zero divisor and non-zero divisor at the same time. Yeah? So we get, yeah, so let me mark it so that if you have zero divisor, we get that so in RG for R we get RG is not zero, and if you have G in RG is non-zero divisor for R, we get that I is finitely generated. I is finitely generated in RG. So actually, in both cases, we get that I is finitely generated. In both cases. And here you take I, you pass to the homogeneous generators, and we can use this homogeneous generators to generate algebra, yeah, because you can do the following. So I is just in order to prove it, to prove now.
You mean that it's equivalent to say that RG is...
Yeah, I'm saying that it is equivalent to say that either, so finite generatedness R as an algebra is equivalent to say that I is finitely generated ideal, since to prove that RG is finitely generated algebra. So we can take, so we have to express homogeneous element of RG in terms of homogeneous generators of R, of I. And you just yeah, so yeah, so just yeah, so notice that that you just have so we have reduced it. So we have yeah. So this element is of course in I. Yeah. So we have we can.
Yeah, I don't know. It's more or less obvious, but no. I mean,
Сейчас. Нет, подождите. Но там это все-таки некоторая редукция, ну вот оператора проектора, да? Ну, в смысле, в тот раз мы делали следующее. Мы брали элемент, ну, как бы расписывали его G, T, F, T. Ну, как бы мы представляли, и как он был конечно порожден как идеал. И отсюда мы, ну, как бы брали проектор, ну, то есть это он сохранял свойство быть инвариантом, ну, поэтому он делал коэффициенты инварианта. Так мы, вообще говоря, не знаем, что коэффициенты инварианта. Нет, извините. Да, это извините, они просто инвариантны, потому что мы же на ДЖ делаем. Да, я неправильно сказал. So this is obvious, of course. Yeah, so since we're taking so a priori, yes. So this is of course being graded. Yeah. So just yeah. So let me write it down. Yeah. So we have again from the beginning you have we are finitely generated not over R but already over RG. So you have precisely H can be expressed as the set of generators, so HI tilde, and this, so Fi are homogeneous elements of positive degree. So and HI are also graded, so they belong to RG, yeah? So are graded of smaller degree of strictly smaller degree than h. So this implies that. So now we have to.
Статья была такая, что если есть несколько компонент,
Да, если, ну, грубо говоря, если есть несколько компонентов, то можно их с помощью делителя нуля, ну, как бы сбитие,
можно прийти к компоненте.
да, к одной компоненте и к другой,
А
да.
потом индукция размерности.
Да, а потом, если у нас компонент нет, то индукция размерности, которая сразу приводит, что может появиться несколько компонентов. То есть как бы от делителей нуля тут не денешься. Ну, то есть обращение в ноль одного элемента может дать гиперповерхность с несколькими компонентами. То есть у нас, конечно, ну, то есть обычно в алгебраической геометрии индукция, ну, я имею в виду в такой, в бирациональной там или еще какой-то, что мы переходим к не особой гиперповерхности, но здесь как бы это гарантировать нельзя, поэтому вот мы переходим, ну, какой попало, и значит, как бы из-за этого нам приходится работать с делителями. Вот. Ну, и как бы у нас в любом случае, что мы видим, что мы доказываем, so in any case we prove that RG is Noetherian, so in any case I will be finitely generated ideal, so here it's induction by dimension, and you prove that this is finitely out of this, knowing that the algebra is graded, we prove that it's finitely generated from finitely generatedness of some ideal. So this is part of the proof. So so now we shall explain Noetherian induction. Yeah? So precisely passing to components. And so I haven't said anything about the module, but we have assumed Noetherian induction to pass to components. Yes, so that's why we have to keep track something on module.
Sorry, it's the sixth page.
Done?
6.
Да, спасибо. Вы технические комментарии можно и по-русски говорить тоже. Потому что я сбиваюсь. Ну, то есть я думаю, что что-то содержательное вы спросили. Yes, so suppose you have R arbitrary and M is Noetherian module. Suppose we have so consider the set of modules for which the module is graded. The module is finitely a module of invariants. G is Noetherian. Noetherian RG module. Yeah, so then clearly, so if you have exact sequence, yeah, so invariance gives you exactness from the right, so passing to invariance gives you exactness from the left. Yeah. yeah. We also. Yeah, so this of course shows you that if so image, but of course we do not have exactness, but if you have here, if you consider image of phi, so it is what? It is submodule of M2. So this is also an Ethereum submodule. So if you have M1 and M2 has this property, has so has star, then so submodule in Ethereum module is an Ethereum, so then M has property star. So also if yeah, so if you have I is now so if M has proper support. So suppose that M has proper support in R. Then by induction, so that means that annihilator of M is non-trivial. Yeah, so is I non-trivial ideal. So we can by induction of the support on dimension of the support. Yeah, so we can assume that all torsion modules are finitely generated. So all torsion, so that it is finitely generated. So MG is an Ethereum. And so that means that you can pass. For any M, we can consider torsion module, torsion submodule. So elements in M annihilated by some R, yeah? And passing to M modulo T, torsion of M up. Yeah, so again we can assume, so we can assume that M has no torsion.
So what do you say here that by induction on dimensional support we can assume that MG is
yes,
Ethereum?
support of M.
Yeah, I understand. What do you mean by it?
Yeah, so support of M is algebraic set on R. Yeah.
Yes.
So I mean this notice. We can say that all so this property star holds for any modules for any shifts with proper support smaller than than R than X itself. Yeah?
Why?
Yeah, это вот там как бы. Yeah, so the argument is here.
Okay.
Is at the next step, because I mean I'm saying the following. So this is yeah. So this will be, because we can. I shall give you the algorithm how we can pass to the support. Yeah.
Okay.
Huh?
So there you say that by induction, so we then we prove the induction, or what? So I don't.
No, I mean so suppose you have R.
Okay.
So X. And suppose the module has smaller support.
Okay.
So let us assume by induction that modules with smaller support has this property.
Why we can assume it? So,
Не, ну да, нет, просто как индукция действует.
я просто не
Что-
понимаю, какая
да.
индукция. Во-первых, сверху, снизу,
Индукция
Да.
по разменности носителя.
Нисходящая.
Ну, что если носитель меньше, то свойство верно.
Окей.
Да.
И мы вот хотим это
Ну,
показать сейчас.
да, самые маленькие носители у точек. Точки
Да.
это просто векторное пространство.
Окей. И мы вот это
Yeah.
хотим доказать сейчас, да?
Да, мы
утверждение.
хотим, мы утверждаем следующее, что по индукции, нет, я расскажу о переходе к неприводимым компонентам носителя.
Окей.
Yes, so there are several inductions. So assume by induction that we know that if module has strictly smaller support, then it has, so MG is finitely generated.
Окей.
So then there are, so I claim that you can decompose the module in the torsion submodule and the quotient, which has no torsion.
Окей.
And by property of extensions, we claim that if we assume that yeah, so this means that property, so torsion of M G is Noetherian by induction. On dimension of the support. And M, torsion of M, has no, so this has no torsion. So if you prove it separately for how to pass to induction on the components and how to say so we have to prove separately, yeah, so for torsion modules and non-torsion modules.
Окей.
Yeah, so prove assumption for non-torsion modules. For non-torsion modules. And non-torsion modules, they have so if you have the set of invariants is non-zero, yeah. So we have embed R maps to M, yeah. So if so then R embeds into M. Yeah, and torsion module, non-torsion modules have rank. Yeah, so that they so you have inclusion of M into M tensor K, where K is a fraction field of R. Okay. And so this implies that you have embedding of R into M, so that allows to pass. So this is invariant. So G equivalent embeddings. So then, so simply so you take element in Mg and you map R into R times, yeah. And so you can pass to this exact sequence, and this has smaller rank, yeah. So this has smaller rank. So assume this property of having Noetherian invariants for the modules of smaller rank, and so by induction on rank, we get that Mg is Noetherian for non-torsion. Yeah. So and now we have to prove it for torsion modules. Yeah? So actually also you have so also we have by induction of rank, also we have to, we are reducing it to the case, so we reduce it to the case that R, so M is equal to R, yeah? And so here we can consider R is, so we can consider parsing to components, and so here, of course, here, of course, just here we have, so if you have annihilator, then so we have to consider the case when, so we have not considered that so precisely we have to consider so we have to prove it precisely for torsion module, so to passing it to Here we consider, so if M has proper support, so you can consider non-trivial annihilator, and we can pass it to, so we pass to the ring R, which is R modulo I, R tilde, which is R modulo I. Yeah, so then we can consider this sequence. Again, we can consider torsion elements and non-torsion ones. So you have. I mean that. We have decreased the support, but you can have non-torsion module, but over the ring I mean R was not reduced. So reduced and not reducible, and we have to attack this case. So consider, so now as we have two reductions, so R tilde, so now M was the module over R tilde. So if you have
Ну, там
Да.
просто чтобы
Да, да.
понимание или нет, ну просто уже ну тут как бы
не, ну тут как бы индукция такая, ну грубо говоря, что нужно все уметь все делать в общей точке, вот, и переходить к модулю с меньшим носителем, да? Но вот переход, и все это делается посредством вот этой точной последовательности, что у нас, если у нас есть модули с носителем меньше, чем m, то это подмодуль, и мы можем как бы перейти к нему. Поэтому можно считать, нужно уметь отдельно работать с этими модулями, и у которых носитель в точности сосредоточен на m. Да? Дальше мы должны уметь переходить, уменьшать вот этот модуль, да, мы его уменьшаем просто, поскольку у него нетривиальные инварианты, можно в него тем самым вкладывать наше кольцо и факторизовать и переходить дальше, да? И
с волной не будет иметь кручения.
Вот я хочу отдельно это разобрать. То есть как. Да.
Для R словной, да, правильно?
Нужно доказать. Да. Утверждается, что тут как бы мы можем, m переходим к фактору, это если r неприводимо, без делителей нуля, то у нас есть, вот такой подмодуль и модуль с меньшим рангом. Поэтому нам остается теперь перейти, мы можем вот это уменьшать за счет фактора по r, и тем самым дальше мы должны перейти к случаю, когда, к индукцию по компонентам r. So now you have induction on the set of components of R tilde, and so you have we have to prove the following. So first of all, we can assume, we can assume that R tilde is reduced so here I mean not elements in M with proper support in R. So we can assume that R is reduced, and so why? So otherwise, so you can consider nil radical. So this is ideal J, and you have filtration. So we have so R is Noetherian, so we have filtration by powers of J. And so like yeah, so actually for any so for module, yeah, so you have increasing filtration. Better to say decreasing. Yeah, and we just know that all Gi modular Gi plus 1 are modules over R mod G. Yeah? So we can assume that they are. So this is this is reduced, and by induction. So we may assume that we have to prove by star property. So for submodule, so we know that for submodule and the quotient we have the required property. So we assume we have to prove the statement when R is G is when R is reduced. Yeah? And now we will discuss how to pass two components of R. And so if R is reduced, R tilde is reduced. So we see that you have a decomposition of 0 into the prime ideals. And notice that G is connected. so in the theorem we assume that G is connected. So otherwise there will be some subtleties about the finite group schemes. So so from the beginning we assume that G is connected. So G acts on the set of, so these are primes and these are minimal primes. So minimal prime decomposition. So only minimal associated primes are these are minimal prime ideals. Prime ideals appear in the decomposition non-trivially. So appear in this decomposition. And we know, so that they are just the set, so Pi are in the set of associated primes of R over R. And so G acts on the set. And G acts on the set of minimal elements, which is finite. So, and actually this set is finite. So G fixes minimal elements. So actually it fixes any elements in the set of associated primes. So also minimal elements. So this now we can consider M in the we can consider it in the following subset. So where Pi belongs to the set of associated primes. This is inclusion, yeah. But notice that each component is armored Pi module, yeah. So we are. Да.
You said that G fixes all.
G acts on the finite set, so this is finite set.
Yeah, you mean that any element G applied to Pi is just Pi, right?
Yeah.
Why is it so?
Yeah, just notice that what is, G acts on the set of associated primes, yeah? Because it is canonical set, so the set of embeddings of R modulo P.
Pi are minimal in this set.
So you do not have to assume that they are even minimal, but if you look at this decomposition of zero, you have to keep track only minimal PIs.
Yeah.
But notice that
So it basically means that GI can't just mix components. It preserves.
it's yes. So if you look at the reducible components, then G acts on each reducible component. Okay? But you can formulate this in more abstract terms. So just through the associated prime decomposition. So notice that the set of So if you look at the set of associated primes of any module, yeah, so this is the set of P in the spectrum of R. Yeah, so such that you have embedding so of R modular P in your M. Yeah, so this means that the element, if you have element H inside G, then you have embedding of HP inside M. Yeah. So this implies that group G acts on this set. If you have action on M, of course. Yeah. So G acts. And notice that this is finite set. So what is more important? So you consider, so you have this finite set, and this means that you have you have this finite set, and this means that just G acts on G is not finite. G is connected group, so it acts trivial on finite set. So so the claim is that this. So if you want to consider, so since P is reduced, since R is reduced, R tilde is reduced, so you have inclusion of M into this decomposition, and in general, of course, it is just a map, and so in general you have just zero has associated. So in more general case you have the following. So you have M is so you have associated prime decomposition of 0. So you have an I associated modules, submodules of M. So associated primary submodules. And you have the following, so you have an I, so intersection of an I, so you have this kind of decomposition. And this implies that you have, so this decomposition implies that you can map M into M modular Ni. So this is this will be inclusion. Yeah. But in the case where you do have, so that there are no nilpotent elements. So since we have no nilpotence, no nilpotence. So this reduces precisely to the case the M is you have inclusion to the corresponding components. Ну, то есть это просто ограничение, ну, поскольку мы предположили, что компонент нету, то у нас просто сам идеал это пересечение. Ну, вот носитель нашего модуля это пересечение этих простых идеалов. То есть primary ideals, so primary submodules are just the PI M. Yeah. So, this implies that this reduction implies that you just we have to consider the case when R is just domain. Yeah. So if we prove if we prove if we prove the statement when R is domain, so R will be just R modulo pi. Yeah? So we are done. Yeah, so that means that star, you have just mg that sits in the sum of modules over domain. Yeah? So these are finitely generated over R, Noetherian modules. Yeah? So, this is just yeah, so now let us do this reduction. So so let us prove that R mod P G is finitely generated finitely generated over K, and this will be the following. So notice that if you have R mod P G and you raise it to the power in some big power, so in P to the power n, this better to say like this. Yeah, so you should be able to, so since we do not know that this is finitely generated, so just take element A from this, yeah, and you raise it to the power, and this belongs to RG PG. Yeah? So this means that this is integral over RG PG. Yeah? So this means that. Да.
Кто такой P?
P это простой диал.
Ну, просто мы уже перешли к R, как бы, мы уже отказались от PI.
Но я как бы тут еще...
Это другой P. P это не PI.
Нет, P это вот как раз тот PI. Я просто хочу сделать вот эту редукцию.
Хорошо, P это
ну, как бы, вот эту, ну, редукцию перехода к компонентам.
Мы теперь в контексте R-фактор по PI, M-фактор по PIM.
Ну, да. M-фактор по PI, а вот от R мы еще не перешли к R. Ну вот, как бы, имеется в виду вот здесь, so M factor just M modulo pi, M is module over R modulo pi. And now I want to prove that this is finitely generated over K, and this will do the job. То есть вот он переход, о котором вы говорите, да, к вот он здесь запрятан, неприводимый компонент. This is done as follows. So notice that if you have E in this set, then AP will be invariant. So this means that R mod PG is integer over this ring. Integral. Yeah. Ну, цело, да. Нет, все-таки integer. Ну, цело в смысле integer. Integral. So any number is integer, any element is integer, but the ring is integral. Yeah. So notice that now we're sitting in the zero divisors. So K is now fraction field. So you do not have zero divisors, so you can pass to fraction field of R mod P, and L is, so assume that it is fraction field of R mod P G. So this is the set of invariant elements, and also K0 is just fraction field of RG modulo PG. And notice that
Sorry, is this real that RG modulo PG is indeed the domain?
This is the main. This is
the rightmost.
This one.
Yeah.
I suppose it's because we consider P as a minimal. Right?
So yes,
It's invariant.
yes.
And,
Sorry.
No.
So yeah, so this is clear because PG is just R intersection, RG intersection with P. So this is prime,
Yeah, okay.
and this is also prime. Okay. So notice that you have the set of elements now which are and this is a subset of this one. Yeah, so L is just the subset of this thing. So you see that so this is finitely generated field. Over K0, and this implies so L is algebraic over K0 is algebraic over K0. So I mean this is just finite generated by assumption because R is finitely generated algebra. Yeah. So even over small k, and L is algebraic over K0. So you have algebraic. So it was integer and this was finitely generated. So this implies that L is finite extension of K0. And then you have the following picture. So if you have
Why is it finite? You mean algebraic?
не, ну в смысле оно но оно алгебраично вот из-за вот этого.
Да, это я понимаю, да.
Но имеется в виду, ну, что если у вас есть подполе, ну, что вы не можете бесконечно много элементов добавить. Оно прям, ну, если у вас, ну, лемма, которая говорит, что если у вас есть большое поле, конечно порожденное, и в нем есть алгебраическое расширение, то оно конечно порожденное. Yeah, so this is, this is lemma. Yeah. I mean, it's not just, you have to say something here. So you have field extensions, and you have now here, you have the ring RP PG, and you have integral closure, so R mod P. So it is contained, so this you can consider integral closure in L. So integral closure. And which is so in this case it is finite module over RGPG, so finitely generated module over RGPG. Yeah, so this is a lemma. Yeah, so if you have the field extensions, so if you have finite extension, and you have A here and B is integral closure of A in L, so then B is finitely generated module over A. So this can be found.
Yes, а вообще положение вообще не кик, да?
Вообще. And ну, это про, как бы это лемма про расширение полей, да? Вот, and so you have to so we have proved that RPG is a subset of integral closure, so it's finitely generated. So this is finitely generated module over A, which is RGPG. So this means that just RPG is finitely generated RPG algebra. and this finishes the proof.
Why is it so? So
Uh,
why if
Ну, под модуль нетера модуля нетер. So this is
что вы знаете, что вот правый неотеров модуль?
Ну, сейчас. Ну что, Аня, типа, да?
потому что нетер, да. То есть у нас это мы доказали. Yeah, so this is not theorem because it is it was a step of previous part. So this is not theorem by first part. So the idea that of course we have used so the idea that if you have this reduction so we have proved the reduction step to the components. So in this in this argument we have proved the ability to take Noetherian induction. So the second, so we have R and M, yeah. So passing to, so we have separate passage to RG and separate passage to MG as RG module. Yeah. So here we, so the trick was that we have passed to, so here we learned how to pass two components, yeah? And decrease the dimension. And here we are assuming that we have this step for smaller dimension. We have, so assuming 2 for smaller dimension. We learned how to pass from R to RG. So we proved that RG is finitely generated. So Noetherian. То есть как бы, ну идея в том, что мы можем, у нас есть техника перехода к неприводимым компонентам, и если у нас R состояла из неприводимых компонентов, то вот мы можем переходить каждый из них, и если, ну и уменьшать размерность, если у нас неприводимо, то мы берем какие-то нули и переходим дальше. Yeah, so more or less I have just said the sketch of the proof, so maybe let us do a short break and we shall.
From which book is this?
Это аппендикс из Манфорта, геометрическая теория.
Самое обидное, я вроде бы ставил будильник, но что-то ни я, ни Ева его не слышали.
Можно спросить?
Да. Ну, то есть, если делите нуля, то у вас ядро, образ нетривиальный по нулю. И ядро нетривиальное.
Да, сейчас. Вот сейчас. Да.
И оба имеют меньше носителей.
Хорошо, это индукс носитель, правильно. Сейчас, мне интересно.
Ага. Вот это?
Да, сейчас почитаю.
Ну, это самое главное. В прошлый раз объясняли. Это на самом деле, ну вот как бы тут оно сформулировано вот так абстрактно, а так это лемма проекторное пространство.
Ну, можно считать, то, что вот если как бы если написано, в частности, если, например, R конечно порожденная, да, то на самом деле для большой степени N, да, вот эта штука, если вести в P степени N, она будет вот здесь вот, вообще вся, да? Вдруг
Не,
это может не зависит, как бы. Ну, если просто конечно порожденная. Правильно?
Если R по I,
Да.
конечно, порождение.
Да.
Но проблема в том, что априори мы не знаем.
Сейчас будет.
Нет, в смысле, R по I же мы не знаем, конечно ли порождение.
Не знаю.
И вот в этом проблема. Поэтому отсюда мы... вы правы, если мы знали, что R по I конечно порождено, тогда
Вот это мы знаем, да, потому что мы воспользуемся по индукции, да?
Да, тут индукция, тут индукция, конечно.
Это просто, я вот немножко сбился. From this is finally generated. Как в точности это получилось? Конечно, порождена над чем? Над RG, правильно? Или над чем?
Нет, просто сама, конечно.
Над К.
Ну да, над К.
Да, сейчас. Почему? Что вы сказали?
Помнишь?
Потому что
Свойство как раз того, что уже, конечно,
вот это конечно порождена, а вот это p степени.
Yeah.
Поэтому у вас полиномы, конечно, порождены не надо своей нападенностью. Ну, полиномы накрывают вот это, конечно, порождены на третьей степени. Мы берем образующие здесь и дополняем.
У меня же сломалась на степи.
Да, я помню, ты говорил, что как так получилось, что из этого зависит.
То есть вот это конечно надо вот это.
Да.
Поэтому вот эта штука конечный модуль не будет. Из-за этого вот это конечно порожденное. Это конечно порожденная алгебра, а это конечный модуль. Давайте я там напишу.
Не, да, я понял, что как бы система, она бывает толстая, тоже
Ага, ну да, да. И вот...
ну, как раз когда не брали, сейчас вроде бы, ну вот вчера ночью я понял, как это хотя бы, какой можно алгоритм придумать, чтобы он выдал.
Правильно, число. Ну вот, о чем ты говоришь, сломалось. Вот починилось.
Нет, ну там, ну, бывает, действительно, что-то, ну, это жуть.
Ну, понятное дело, что положительные характеристики это же...
Значит,
И тут еще не было посвящения А. Тут еще не было А. А, все, я здесь. Ага.
Скорее всего, будет не отношусь, ну давай.
ну, например, ты можешь применить уровень по одной координате, по остальным не применять. Там
Вот еще такой вопрос.
будет быть.
Я немножко забыл, что будет, как бы, имеется в виду.
Поэтому там всегда одно и то же происходит.
Сейчас что значит
Как мудрый над
Ну, это без поручения,
да.
да, ну просто... Да. Ну, я...
Да, сейчас просто...
Ага. Только толстая точка, очевидно. А у всего АН, только это АН, не толстая. Что АН не толстая.
Ну, нет, это очевидно, по моему мнению. Но что ты эту схему не можешь взять, потому что ты...
Ну, как бы видишь, посчитать то, что
Нет, потому что толстый...
R сломано уже как бы...
Вот схема бывает.
Ну, как бы domain, да?
Да, но тут просто как с волной это domain.
Да, то есть мы
Нет, ну это как бы, потому что если не domain, то мы могли вот так же.
Хорошо.
Это то же самое.
То мы могли...
Да.
То были...
Одинаковые вещи сдает.
У M были бы компоненты, которые были бы модульны.
Ну, следующий будет да. А как это?
Ну логично. Хорошо, да.
Поэтому можно считать, что та часть R, которая действует на M,
То есть, как бы...
ну что, давайте продолжим, а то у нас такое. Also, I want to have slight comment on the associated primary decomposition, so if you don't mind. Yeah, I thought that it's better to put the induction like this. So here, M is embedded in. So if you have associated primary decomposition, so these are primary submodules of this form. Also, you know that the set of associated primes of M modulo Ni, it is the primary submodules, so it consists only on the corresponding pi. So annihilator, so notice that annihilator of this module, so just G is connected so that it preserves the composition, the composition. So the thing is that why we really use the minimal associated primes. So I wanted to say that Z preserves the set of all associated primes, But if you are speaking about the composition, so if you are speaking about Ni's, so that means that G preserves only Ni's that correspond to minimal components. So that is important because the associated prime decomposition is not unique. So also one can just give you example that associated prime decomposition can be infinite. And preserves minimal components. And since notice that if you're speaking about minimal components, you have annihilator. It contains so it is precisely QI, just P primary ideal, Pi primary ideal. So radical of QI is precisely P. So this means that this module, just a second. Yeah, so you have this, so radical of QI is P, so M modulo P is annihilated. So it's important to notice that elements of M are annihilated by P, by powers of P, but not by any other Pj. So they so M and I. So if you have M that belongs to M and I, M is annihilated by powers of P, but not annihilated by Pj. And this shows that radical of this is precisely Qi. I mean, if you think of the elements, the set of nilpotence elements. So you have, so this module has filtration by powers of Pi. Yeah, so this, precisely already this module, so has filtration by powers Pi k times M and I. And then you can pass to filtrate it and pass to the module which is precisely annihilated by Pi, and it is just a direct sum of R modulo Pi. So yeah, so this is the remark. I mean, you have to prove something, but this is some commutative algebra. So let me now pass to lunar slice theorems.
Извините, просто это первая страница, мы в середине добавили эту страницу, удалить и потом перейти к самопринятию.
Сейчас очистить или что? В середине?
Да.
А как?
Ну, мне кажется, проще далее.
Ну ладно, нет,
просто
проще
пускай
пойти
тут будет
в
свободная
нет,
страница.
ну пусть, да. Проще пойти в конец. Да, и какая, 11 или нет? Какая тут? Это тоже.
13.
Да, 13. Yeah, so let me now pass to more interesting topic, lunar slice theorem. I so we stopped at some technicalities. I mean, they are not so
Всего
interesting.
15 страниц, это так
А?
должно быть. У вас просто всего 15 страниц, это должно быть.
Да, но там одна пустая.
Да.
Это 14.
Тогда 15. Да.
Нет,
14.
сейчас. Тут должно быть 14, действительно,
Нет.
скорее всего.
Нет, да, наш четно.
Сейчас нет, погоди. Первая, вторая, третья,
А,
четвертая.
13. Мы тут должны были. Да. 14. So, let me.
Вот оно, как математика.
Вы пока отошли, так сказать, мы тут все уже напортили, да. So lunar slice theorem. So let me let me start with some motivation, and this motivation is comes from a smooth manifold world, and actually one can also if we pass to lunar slice theorem, we shall understand that. So you can move from take C infinity world of the world of smooth manifolds. So we will have a motivational theorem for lunar slice theorem, and then if you apply lunar slice theorem for algebraically non-closed field R in some particular case, you can sometimes prove the theorem for algebraic smooth manifold. Yeah. So it's not just it's not just motivation. It is also some kind. So this is reflection of that the worlds are connected with each other somehow. So suppose K is a compact group. So X, acting on a smooth variety, smooth manifold over R, and then your smooth manifold X. So, ну тут давайте M поставлю, чтобы миры не путались. Yeah. So what you have? So of course, so you will have you will have an orbit of K. Yeah? So you have a point X, and you have Kx, and this orbit is just K modular L, where L is a stabilizer, and it's also a compact subgroup. So stabilizer of X, so also compact, of course, because it is closed. So the question is, can we define invariant structure of the neighborhood? Yes, so if you have manifold, of course you have always tuple neighborhood. Yeah? So tuple neighborhood is just local, so it's a neighborhood in the normal bundle. Yeah? But the question is, so how we are proving it actually? So in order to prove it, you have to choose a metric, yeah? And you just take in each, so you cover your manifold in the small charts, and so you can take normal direction, and if you have metric on the whole manifold, you can look at the geodesics that look at this normal directions. So normal, epsilon neighborhood of orbit is expand by geodesics that for directions that belong to normal bundle, normal direction of x. And normal direction is just so you have a tangent space of your manifold. You can you have a metric. So by the metric you can decompose it as a tangent space to the orbit or to the submanifold, and you can decompose it, take an orthocomplement, and this will be a normal bundle. So this is can be taken as orthocomplement. Now with respect to the metric. So you take the sort of complement and in each, so that, let me draw it. So you have tangent space. So we do also tangent space of M, and this is normal direction, and in this normal direction you can take the small ball. Okay? So so you can take the in this normal directions. So you can take a ball B epsilon. So geodesic ball of radius epsilon. You just consider all geodesics passing. So so you have a direction, you can consider geodesic, and you can consider the epsilon length on the geodesic. Yeah. So why this? So this will give you. So if you do it, in each point of the orbit, this will give you epsilon neighborhood of the orbit. So just. And the question is, can we describe? Yeah, so also what you can do. So also, so if you have G is metric, G is metric on M. Yeah, so you can consider it's you can take the metric and take the averaging of this metric. Yeah? So we can take the integral over K, where you are acting by K star on the metric. Yeah? Yeah, just by taking. So let me call G tilde of psi and eta. Eta are vector fields. So you can consider the action of K on the vector field and taking metric, so you can average all this product. So it is in the point x. Yeah? So
integration with respect to Harnager. With respect to Harnager on K.
Okay, yeah. So now this what it shows us that yeah, so the metric, of course, here is taken on the point x, and this is taken on the point kx. So this gives you k invariant metric. So can be made k invariant. So this, if you think of the epsilon ball, the normal bundle will map to the normal fiber will map to the normal fiber, and and epsilon ball will map to the epsilon ball. And so this means that k of mx will be mapped to the complement. And if you look at epsilon ball, so k of this ball is just the ball calculated in x. So this shows you that the neighborhood will be k invariant. So neighborhood, constructed neighborhood, will be k invariant. So you may map, so in order to describe structure of this neighborhood, you can map a k times this epsilon ball to your variety simply by the product. And but notice that there will be the points that will map to the same thing, and ambiguity will be the following. So notice that if so by construction, epsilon balls lying in different points of k will be different. Yeah. So this looks like the following. So if your k tau is equal to k1 tau 1 is equal to k2 tau 2. Yeah? So for different balls. So this will imply that by mapping that tau 1 seeds is obtained, of course, by k tilde tau 2, where k tilde is just, of course, k2, k1 inverse. But what is more important, that tau 1, tau 2 should be, so this one and this one should be, so you can consider when points are glued together. Yes, so you can consider that k I are the elements of k, and tau i's are the elements of the ball epsilon. And if you have equality, of course, so that you have, you should, you should have a ball. I mean, so since balls are disjoint, they can have either be disjoint or coincide. Yes.
That's right. Still a question.
No.
Is this map really well defined?
Yeah. So of course, if the balls are sufficiently big, radius, they become intersected. Yeah.
Or they may be
So,
undefined. Or they may be undefined actually.
They may be not a ball. Yeah. So so here, of course, I should also.
Просто такой юридически может не быть такого размера.
Да. Ну поэтому, also I should have to make the following remark, so that it's more convenient to think of the ball in the tangent space. Yeah. So you have this map from K. So the ball sits inside an epsilon. Yeah. and you may map first of all the ball to exponent. So in order to make so let us consider this ball as a ball in an epsilon, and so you can map the ball like this. Yeah, so you can take k and epsilon, and you can take exponent. Exponent, it is just the geodesic map. Yeah, so this is a map, a geodesic map. And then you map it to the variety via to M via the product. Yes.
And for this, we choose a point on the orbit.
Нет, ну в смысле, что да, мы стартуем с точки X на орбите исходной, берем, выбираем, so n epsilon, ну в смысле nx, извините, nx тут должно быть написано. И ну как бы в nx будет свой открытый шар, so you have so in nx it's a vector space. So there is standard vector space metric. So G gives a metric, gives a norm on vector space, on the vector space. And B epsilon is standard, B epsilon tilde is standard ball. And you can map this standard ball by a geodesic map, yeah, so to M, and then to apply psi just B epsilon tilde is I will call it B epsilon, yeah. No, I would like to call it M, for the reason is B epsilon is just exponent of B epsilon tilde. Yeah? So if this epsilon is sufficiently small, then geodesic map is injected. Yeah? So if epsilon is sufficiently small, so geodesic map is injective. Yeah, so just of course if the ball is so you just have direction, so you just have a standard ball, you have standard directions, standard vectors, so these are intervals, and then they map into geodesic. So this is B epsilon tilde, and this is B epsilon. And of course, if you think of sphere, yeah, so you have example when if the geodesics are too long, they can even just intersect in one point. Yeah. So but we can take a sufficiently small map, and also we can think of the following. So we can consider this map phi, and the differential of phi is just consists of taking Lie algebra. So it's a map from tangent space. So for the Lie algebra of K times this ball B epsilon tilde to the tangent space of M, and this is just a sum of tangent space to group and tangent space to epsilon via the so if you have vector field eta and psi, yeah, so this maps to vector field eta x plus corresponding psi of x. Yeah, so this is vector field. So this is differential in the point x. Yeah, so this is value of differential in the point x. And this means that if this differential by our choice, the orbit k maps to the tangent space of the orbit, psi x was taken in the ortho complement. So this is just isomorphism. So this is isomorphism by construction.
Сейчас.
Ну просто вот в окрестности, да, ну в окрестности мы взяли, но это просто как бы дифференциал, ну в окрестности единицы k, а это просто, ну, шарик ортогональный.
Нет, можно склеить
Вот.
касательное пространство L. Да?
Да.
Можно склеить касательное пространство стабилизатора.
Ну да, там.
Да, не, но я же сказал, что это, в смысле, вот, да, я неправильно сказал. Нет, не изоморфизм, а сюрреактивный, да, ладно. Субмерсивный, да. Subjective. So, notice that if you like in K, in the group K, you also can decompose it, so you have a subgroup L, and here, if you like, you can decompose it in the tangent space to L, yeah? And take the complement as the tangent space to the orbit. Yeah? So you can take the normal bundle isomorphic to tangent space to the orbit. And so if you take this kind of thing, then so this will be a surjective morphism. And notice that it will be equivariant. So it will be surjective in one point. It will be k equivariant. So this will be it will be surjective in all points of the orbit. Yeah. So notice that. Да. So phi will be surjective in all points of orbit. K, and so in the I mean in the neighborhood. Yes, so that you can take. This means that you can take sufficiently. So it will be equivariant. So you can take also the neighborhood. Yeah. So you can think of this differential. So. It will be surjective, and it will be a yeah. So now let us consider this map. So k times b epsilon tilde. So this is equivariant. Yeah. Notice that stabilizer L acts on the normal bundle. Yeah, so because we have done it, so since G mod G, so tangent space to the orbit is L stable. So then since T of x K of L is L stable, and metric is L and metric is L K, and hence K invariant, and hence L invariant. So the ball B epsilon is L invariant ball. So this means that B epsilon tilde is L invariant ball. So this shows that yeah. So if so choose yeah. So now we are also able to choose a different epsilon. So let us choose epsilon in such a way that so you have neighborhood of the orbit, of course. Yeah, so U is neighborhood in the orbit in K model, and Kx. So better put a note about Kx of x, and we can assume that phi is just phi submersive on this, so is submersive on U can be epsilon. And this will imply it is so if you restrict if you embed U into K, yeah, so some lift transversal to L, so but you will have we have embedding U times B epsilon embeds into M, and then you can simply by equivariance, so it is embedding in one space, but you have in the neighborhood of one point, but you have K equivariance, so by yeah, so I mean that by choosing, so I will write that we can assume this that phi is submersive, and this is embedding by choosing sufficiently small epsilon. And so by K equivariance of all maps, so phi will be submersive in all points of the orbit. So phi is submersive in all points of the orbit. And by compactness, we can choose by compactness of the orbit. We can choose epsilon such that if you have K psi is equal to K1 psi1 is equal to K2 psi2, that so simply that you cannot have the property that if you have different points, so x, and here you have kx, so k1 x and k2 x, so this epsilon balls cannot intersect. Yeah? So you cannot have that epsilon balls here. So this is B epsilon K1 of X, and this is B epsilon K2 of X. By being submersive, they cannot intersect. And this implies that by being local isomorphism and equivalent map, they cannot intersect.
Well,
So
unless they're the same
unless they're the same, yes. So this implies
modular L.
that I would say that K1, K2, K1 minus 1 belongs to L, so it stabilizes. So I will write it like this, yeah? So like K1x is equal to K2x, so the point is the same, and in this case Xi1 is equal to K1 K2 psi x. Yeah? So this so since these are the same, then this implies that K1 inverse K2 is in the stabilizer. So of x. And the stabilizer moves Xi1 into Xi2. So this tells you that the object that we are mapping actually is the following, so that can be described as follows. So this is notation. So this is a set of pairs due to this kind of relation. Yeah, so K1 Xi1 is equivalent to K2 Xi2 if I would better write down by the quotient that equivalence is just a multiplication by L and L inverse of Xi. Yeah? So we're saying that the following points are, it's more convenient to recall it by this kind of relation, yeah, so that if you have, so that means that the product of K inverse and this one will be inside L, and Xi will differ precisely by this element. So this is called homogeneous bundle. And this will, so from the viewpoint of geometry, it's convenient to say that, yeah, so the following, so you have...
So, sorry, it's diffeomorphic to normal bundle to the orbit, right?
No. Не, ну в смысле, что это скорее окрестность, да? Yes, so our theorem tells you that this thing will be just the tubular neighborhood of the orbit.
Ну, шар, diffeomorphic, как РФ, ну в целом это правда нормально.
Ну да. So, не, просто какой?
А?
Не, ну у вас какой шар, открытый или замкнутый?
Открытый же у нас.
Ну да, давайте пусть открытый.
В смысле, он многообразен?
Но в смысле можем и замкнутый отобразить. Ну, и я когда тут, я поэтому и не сказал да на ваш вопрос. So geometrically you have So if you have this product, you have standard projection, so you can take k in this pair, and you can map it to k modulo L. Yeah. So this this is a k equivalent map. And the fiber is, of course, all the ball, yeah, so in this variety. So you will, that's why it is called homogeneous bundle, because it is a bundle over K mod X with the fiber B epsilon. So, and what is good, yeah, so this is what you can say about the lunar slice theorem. So in compact case, this tubular neighborhood is just isomorphic to K, this bundle. Yeah? So the question what you can do in the world of algebraic varieties. So there are several problems about this. So let me formulate, say some questions. So how to formulate it? So so can we do it with for arbitrary x? Yeah, so arbitrary x. So the question is then when can we do it? Yeah, so the answer here is no, actually.
Sorry, a question about it first. So the
Yeah.
theorem, the actual statement of the theorem is that we can make the tuple neighborhood sort of homogeneous.
Yeah. So the claim is that the tubular neighborhood is homogeneous, has homogeneous structure, and so there is a description. So the question is, can we generalize this to algebraic varieties? And there are many questions about this. So first of all, there is no tubular neighborhoods in the algebraic world. So the problem is that you cannot compare normal bundle and the variety itself. Yeah, so because you do not have the map of normal bundle in the ambient variety. So of course there is some kind of some methods to avoid it. So the so-called degeneration to the normal cone. But this is the generation. So this is not the subspace. And the lunar slice theorem is a stronger result. So you pay the price so that you do not have epsilon neighborhood, but one can think about, so here you can think of the following. Suppose you have analytic variety, and you can think that K acts analytically. And this theorem has analytic counterpart. So the ball is taken in as some open neighbors. So that this normal bundle is normal, just this ball in the normal direction in the analytic version of this theorem can be made analytic variety, and then you have analytic isomorphism. And the trick is that when you are speaking, this is the origin of the Taut cohomology. Why we are thinking about the Taut cohomology? Because analytic neighborhood. So in order to define analytic function, yeah, so you have to extend it. When you are doing extension, you can return to initial position. So in order to change analytic category, you have to change the word analytic and the small neighborhood to the word covering and a tall neighborhood. So the neighborhood will be sufficiently big, so it will be the risky neighborhood, but then your object is not has isomorphism on this the risky neighborhood. But you can think of that you have a tall neighborhood, so you have a tall map to this risky neighborhood, and you have something for base change of this.
But it is a big lot where you can do this.
Yes, of
But
course.
usually analytical becomes formal in those break words.
Yes,
Italic
yes,
were very
yes.
lucky.
And this is precisely the place where some miracle occurs, and as you have noticed, you cannot do it in any case. So there will be at least some conditions on the variety itself and on the orbit, etc., etc. So we have to impose some conditions, but after imposing some conditions, we will be able to formulate the analog of that theorem and algebraic setting. So this is precisely Luna's last theorem. So let us to be continued.
Как бы будет редуктивный или любой тоже получится?
Нет, G будет редуктивный, более того, стабилизатор будет редуктивный. Это не прям, ну то есть это как бы и везде есть контрпримеры, то есть если как только мы отходим от
А что ты номером будет?
афинность. Ну то есть как бы это важно, то есть, ну как бы мы поговорим уже.